Um, Section 4.1 is basically radian and degree measure, which I would also just rename angles. Like it's all about the basics of angles. So radians and degrees are the two ways that we can measure angles, much like we have multiple measurement systems for length. Like I could measure in inches or I could measure in centimeters. We all have to agree on this idea of angles in standard position. So this is something you should have seen in Algebra 2. This angles in algebra and pre-calculus and these types of classes where we're dealing with functions, we're going to fix them to the coordinate plane. So we've got an x-axis and a y-axis. As opposed to in geometry, you just have angles out in space, right? Just anywhere you want. Every angle in standard position has its initial side at the positive x-axis. So all of your angles are going to start going to the right on the x-axis. Okay. And then they can open counterclockwise or they can open clockwise. Okay. And they'll end at some other ray or side of your angle. That's called your terminal side. Now, the terminal side, you know, when you're sketching angles for me, I'm going to be checking, like, is your terminal side in the correct quadrant? So this terminal side is in quadrant 2. Sometimes the terminal side may land on one of the axes, and then we call that a quadrantal angle, like if it's 0, 90, 180, 270, so on and so on. And you can even have the terminal side be the same as the initial side. Okay, so just kind of make note of that. If your angle opens counterclockwise, it's a positive angle. I always thought when I was first learning about angles in standard position, that seems counterintuitive to me, to go counterclockwise. But now that you learned it, this is not your first go around. Okay, now that you've learned it once before, it probably seems pretty normal to you. Yeah, when it opens up, it's a positive angle. And then negative angles open clockwise. So based on this picture, you know, that little red arc, I'm going to want to see you draw that so I can tell what direction you're opening your angle. I can see that that must be a positive angle. If I were estimating that angle, I might estimate it like 130 or 135, something like that degrees. One thing that's going to be most challenging for us in pre-calculus is making the switch over to radians. So a lot of times in Algebra 2, students will take something in radians, convert it into degrees, do the work that they need to do in degrees, and then change it back to radians. But this is potentially your third or fourth go-around with radians. Geometry, Algebra 2, pre-calculus, and maybe if you had Algebra 3 in there. So we really want to be able to skip the conversion step and just work in radians. Let's be comfortable with this idea of a radian. So that's one thing that you can really challenge yourself with if you've always done the conversion. Try to just work with the radians. It might be uncomfortable at first, but hopefully you'll get better at it and you'll know what kinds of questions you need to ask. So next up, I'm going to talk about the radian, and I have a definition, and I also have this animation here at the bottom of the screen. I'll talk about the animation after I give people who want to write down the definition a chance to write that down. That way you can write, and then you can focus on the visual. I have things underlined and colored in the definition only because for me, when I'm trying to understand that definition, those are the separate phrases that I really need to focus on. What does that part mean? So that once I understand that little phrase, then I can move on to the next piece, and that puts it all together. But I will say, for me, a radian makes way more sense when I see it visually. So I'll give you a chance if you want to jot down the definition to jot some things down. so either method of measuring an angle is really okay, degrees or radians. A lot of times when you get up in higher level math, you're going to see things more often in radians. Some people will prefer radians because like the idea of a radian actually comes from a circle, whereas degrees are kind of like man-made units. We decided that there were 360 degrees in a circle, and this is how we would break it up. Okay, but degrees really come from the actual circle. So 1 radian is the measure of an angle. Always remember that even though in the picture you're going to see arcs, that a radian is actually the measure of an angle, not anything on the circle. Okay, so it's just like a little degree. It opens up so much. The intercepts in the length of an arc of length r, where r is the radius of the circle. So we're going to see that in this image. We're going to draw some radius, could be any size, and use it to draw the circle. Take the radius and fit it to the circle on the outside. So you got to curve it. Whatever arc that intersects, okay, that angle, that's 1 radian. Okay? And then you could keep doing that. Same arc is 1 radian. 3 plus a little more, or pi radians, is 180. Therefore, 2 pi radians is 360. And it doesn't matter what size circle you have, you'll always be able to fit 2 pi radians. Okay, whatever that radius is. You could go home and practice it if you wanted to. Does anybody recall in Algebra 2, like how many degrees are in 1 radian? Or if you're looking at the picture, how many degrees-ish is a radian?
57.
About 57, yeah. It even makes sense. Well, you can see here, it looks close to 60-degree angle. And then it makes sense if you think about it, like you can get a little over 6 radians in 1 circle. So we know that 1 circle normally has 360. If we divide that by 6, that would be 60, but we can get a little bit more than that, so it must be less than 60. So 57, 58, somewhere in there. Okay. So it's just another way to measure an angle. This is a picture that you may or may not have seen before with all these special angles listed. You don't need to copy this down. I'm going to provide you with a little slip so you can have it in your notes. Now, we'll talk more about these special angles when we do the unit circle on Thursday. And some of you are going to look at this and be like, oh yeah, I remember all these angles. And some of you are going to look at it and be like, oh, I don't know where all these angles come from. That's okay. Pods have tape, so if you want to take this into your notebooks, you can, and then pass the tape forward or backwards so other people get an opportunity to use it. So that group has tape, that group has tape. Yeah, they'll pass it over to you. So notice, like, obviously as you're, like, looking at this yellow piece of paper, not all the angles on the circle are listed, right? We're missing 1 degree, 2 degree, 2.5 degree, etc. The only angles that are listed on this circle are what I would call the special angles. And to determine, like, what are the special angles, really focus over here in quadrant 1. These angles in quadrant 1 should sound really familiar to you. 30, 45, 60, 90. Those are the angles that are the special right triangles, right? 45, 45, 90, 30, 60, 90. So when we do the unit circle on Thursday in 4.2, we'll see like why the other angles are there, why we chose 120, 135, 150 in quadrant 2. Okay, but these are just the special angles and their radian counterparts. Okay, so at some point you'll know all these angles because you'll have memorized the unit circle. I wanted to give you this image so that, like, today you'll be asked to sketch angles. When I ask you to sketch an angle, I really want you to make sure that your angle is in the right quadrant. And so if I'm sketching angles, rather than using all of these angles on this image, I really focus only on my quadrantal angles. Okay, so those are the ones on the axes. So if I'm sketching something in degrees, I might be looking at these values, like 120 is going to be between 90 and 180. Okay? If I'm sketching something in radians, then I'll be looking at 0, pi halves, pi, 3 pi halves, and 2 pi. And each of those you can even continue further, just like we have positive and negative angles going in opposite directions. You also saw in Algebra 2 where you could have an angle that has a whole spiral. It goes around 2 times and then some. Okay, so you can even continue this. Like if I was at 360, just add another 90. This could also be 450, and add another 90. This is 540. So if I want to graph a 500-degree angle, it's somewhere between 450 and 540. Okay. So I really focus when graphing only on these quadrantal angles. And I just want to make sure that you get it in the right quadrant. I'm not going to be looking at Brian's and be like, that's definitely not pi over 5, that's pi over 6, how dare you. Okay, I'm not going to look that carefully. I'm just going to see that Brian put it in quadrant 1. Okay. Okay, so what I want you to do with your group is see if you can graph these 4. I'm going to just pick some pods to put their work up on the board as they get them done and agreed to. So there's 2 in degrees and 2 in radians, and I just want to see if you can plot that terminal side in the correct quadrant, wherever that may be. And, I think probably the biggest conversations are going to happen when you get to radians. So make sure you talk with your group and share out ideas. Some of us feel more comfortable with that than others. Just a quick sketch. It doesn't have to be the most fabulous drawing that you've ever drawn. It does? I don't know what happened. Maybe got dusty from the winter break. Maybe my computer is dying. That's fine. I like the spirit from you guys. Okay, so I will slide these up so you can maybe get a better look at them, and we'll see if we agree. So for the 2 degrees, 225 and negative 120, are we okay with that? Both in quadrant 3? Okay, thank you to all the drawers. You guys gave that little arc showing us the directions. So we can see 225 is opening counterclockwise, which would be positive, whereas negative 120 looks to be negative, opening clockwise. And, you know, like, that's that whole idea of I'm not going to be super picky and be like, oh, 120 looks more like 135 and 225 looks more like 240 or something like that. I'm not going to be super picky when I ask you a graph. Okay, so that looks fine. I agree with both of those. Let's talk about 3 pi over 7. So that was Nate's group. How did you guys decide quadrant 1?
Because it was like, we did it because it was like less than, like, what was it, 1/2 pi or whatever it was. So.
Yeah, okay, so remember I said when I'm graphing, I'm going to focus on quadrantals. And so I would be thinking about 0, pi over 2, and pi. And I could keep going and label all of them, but wouldn't we all agree 3/7 is between 0 and 1? You don't have a full candy bar if you have 3/7 of the candy bar. Okay, so we at least know it's less than 1, and then you've got to narrow it down even further to either quadrant 1 or quadrant 2. Do you have at least half of the candy bar if you have 3/7 of the candy bar? And Dylan, you guys are saying no. What would be half of 7? 3.5. So if you only have 3, you're short of a half. Therefore, your angle should be in quadrant 1. Now, we might argue it's closer to the pi over 2, but that's fine. Okay, it's in quadrant 1. Okay. Good. And then 7 pi over 3, how did you guys decide in quadrant 1 as well?
Because it was greater than 2 pi, it had to go more than one full circle, but it was less than pi over 2, so it had to be the first quadrant.
Okay, so before we were looking at 3/7, and we were looking at that in comparison to like 1 pi. It's less than 1 pi, and then it's even less than half pi. So it's in quadrant 1. Now we're looking at the fraction 7/3. Well, 7 divided by 3 is 2 1/3. So we could get 2 pi in. That's why I actually drew the full circle, and then we still have a 1/3 pi to go, which would leave us in quadrant 1. So you can graph angles in radians without doing a conversion. You just need to think about it in terms of how it relates to those numbered pi's. Now the only difference would be if you were given a radian that wasn't in terms of pi. Then you would have to think about whatever pi divided by 2 is, like 1.57. So if I got a radian like 0.76, and there's no pi and there's no degree, then that's 0.76 radians, and that would be between 0 and 1.57, which is half of pi. So it would be in the first quadrant. Okay. But most of the time when I ask you a graph, there'll be a pi there, if not always. Good. So something for us to practice tonight. Okay, next up, I am going to give your group a card, and on your card is a specific topic that you should have already talked about in Algebra 2. You are going to brainstorm together and see what you can recall, if there are any formulas or numbers that you need or just what it means. And then if you're really, really stuck, you might, pull on your resources, like Google, to get some kind of something to say. So, see what you remember. And then we're going to go through each one, and you'll share with us.
Yep.
Did all the groups get a tape if they needed it?
Well, you can try it with one of these.
Oh, yeah.
their area of a sector card. There are two formulas that exist, but we're going to do the one in radians.
Land on each other. It's like
I'll ask you just to share what you know.
Yeah.
So you'll give me some feedback.
Yeah. Wouldn't it just be radians divided by pi because radians is already in terms of pi? And then that makes
Okay, let's come together. Seems like our conversations are kind of dwindling here. So the first topic that I have is conversions. From degrees to radians, radians to degrees. Is that my group right here? Okay, so tell me what you remember, if anything, about converting degrees, radians, vice versa.
For degrees to radians, we have the degree divided by 180 times pi.
Oh, yeah. So the degree divided by 180 and times pi. What did you say for radians then? Or to go from radians to the degrees?
Pi radians times pi times 180.
Pi radians times pi. Okay, I'm going to go back up to this first one. So, does anybody else recall conversion? Degrees to radians? And maybe just like say it differently than Maddie does? What were you going to say? Yeah, it's really just like take your angle that's in degrees and multiply it by pi over 180. So, I mean, like, that's essentially what you have, right? Your angle in degree times pi over 180. So I'm going to say multiply by pi over 180. So if you want to go the reverse order and you want to change from radians to degrees, you'll multiply by 180 over pi. You'll flip that fraction. Okay, so multiply by 180 over pi. So you could say, you could take your radian angle and you could, I would say you would divide it by pi and then multiply it by 180 is what you want to do. You want to do your version. But yeah, essentially they're the same thing. That's called just a conversion factor. It's the same way, like, what if you have something in feet and you want to turn it into inches? Then you multiply by 12. But what if you have something in inches and you want to change it into feet? Then you divide by 12 or multiply by 1/12. So you're just using the reciprocal conversion factor. And pi over 180 works because we know there are pi radians in 180 degrees. Does anybody have a good way to remember, like, which one to use? Like, how do I know if I'm going to multiply by pi over 180 or 180 over pi? Dylan?
Well, if you're going to radians, you normally know there's a pi on top, so pi should be on top of 1 degrees to radians.
Okay.
And then same thing for radians, where if pi is on top and it's pi on bottom, it
Okay, yeah. I mean, like, not all radians have to be in terms of pi, right? So you can have decimal radians. Like, if we multiplied by pi, it would be a decimal. So we have to be careful with that. But I think you're on the right track there. You want to cancel out degrees, so degrees has to be on the bottom. Radians has to be left on the top, so that's what I end with, which is the pi. If I want to cancel out radians, then I got to put radians on the bottom, which would be pi, and I'll be left with degrees on the end. Okay, good. So I've got two examples that I'll just run through real quick. I'm going to convert 225 and 2 pi over 5, vice versa. So for the 225, we're going to take our angle times pi over 180. If you want to practice in your calculator, I have it over here on this sideboard. When you give me radian answers, I always want it in terms of pi. So don't type pi into the calculator. It will multiply by that decimal, 3.15 or 1415, etc. And we don't want it to do that. So you would just do 225 divided by 180. And you can hit math fraction and it'll spit out a fraction for you right away. The other method you could do is just like simplification, right? So 225 and 180, I know that those both reduce by 5, so that's 45 over 36. And then when I look at 45 and 36, I know those both reduce by 9, so then I'm at 5 over 4. And that should be the fraction that your calculator gives you, right? 5/4. So generally we see the radians written as fractions, so you can mimic that by using your fraction button in the calculator. When I want to go from radians to degrees, I multiply by 180 over pi, so that degrees will be left over, the radians will cancel. And most often they'll have pi in them, so the pi's will cancel. That doesn't always have to be true, but most often they will. And I could do this one, you could type it into your calculator if you wanted, but I can also just simplify it. That's going to be 72 degrees. It won't always work out to a nice even number. Sometimes you might have to have a decimal. That's fine. Okay, it's no big deal. Okay, round if necessary. Questions, concerns on conversions? Okay, pretty straightforward. Next topic. Oh man. Those of you who didn't have these cards, do you remember talking about complementary and supplementary? It's maybe been a while. Okay. But you may have even learned like the definition of complementary and supplementary even before geometry. You maybe came with that knowledge to geometry, so think about how much you know. Who had complementary angles? Okay, what do you guys remember about complementary angles?
That they add to equal 90 degrees.
And now you could add what kind of knowledge from Algebra 2 and Pre-Calculus?
4 pi over 2.
Excellent. So if we're ever asked to find a complement, we can work either in degrees or in radians. Usually your brain works best in degrees, so I'm just going to say, like, give an example here. What if I said you have a 20-degree angle? What's its complement? How would you find it? Subtract it from 90. 90 minus 20, 70 degrees is the complement. So in degrees, we just do 90 degrees minus the angle, and I'm using theta there for my stand-in angle. Then I'll get my complement. If I do radians, we want to move away from what we maybe did in Algebra 2, which was convert it into degrees, then subtract it from 90, then change it back to radians. If we want the complement of an angle in radians, then instead of doing 90 minus the angle, we'll just do pi over 2 minus the angle. That's fine. No big deal. So which version you use just depends on which way your angle is written. Good. Which group had supplementary? What do you guys remember about supplementary?
We said it's two angles whose sums add to 180 or pi.
Yep. 180 or pi. So same sort of idea. What if I tell you the angle is 50 degrees? What's its supplement? You would do 180 minus your angle. And so if we were to switch that over to radians, we're just going to change the 180 to pi. So we can do it in either version. Complements and supplements. Now I'm going to put a little side note here. For both of those, well, we all agree that there are such things as negative angles. When we're talking about those two angles whose sum is 180 or 90, we're thinking more geometrically like angles in space, and so we actually want the angles to be positive. So you won't, like if you had like a 190 degree angle, there's no complement and there's no supplement, because it's already more than both of those. So if you ever get a negative answer, just say there is no complement or there is no supplement. Now, I would say everybody's probably going to ace it if I ask complements or supplements in degrees. So let me, of course, practice one in radians. Now, this is the same angle that we just converted, right? 2 pi over 5. We said it was 72 degrees. So I could easily make the conversion and do complement and supplement. But I want to encourage you in pre-calculus. If I give you an angle in radians, work in radians. Okay. So find the complement. Normally I would do 90 minus the angle. Now I do pi over 2 minus the angle. 2 pi over 5. In order to be able to subtract, what will I need? Common denominators. Those are fractions. So a good common denominator for 2 and 5 is 10. That's 5 pi over 10 minus 4 pi over 10, which is pi over 10. Not negative, so it's a good complement. I multiplied this one by 5 over 5. I multiplied this one by 2 over 2. To get the supplement of the same angle, instead of doing 180 minus the angle, because it's in radians, I'll do the equivalent to 180, which is pi minus 2 pi over 5. Now for supplements, you could get common denominators if you wanted to. That's like pi over 1. But it's also really easy for me to subtract. 1 pi minus 2/5 pi. I have how many pi's left over? 3/5. Okay, so I don't work too hard there. 3 pi over 5. That's still positive, so it's good. If I add 3 pi over 5 and 2 pi over 5, they'll equal pi, the sum of supplementary angles. So it all works out. Okay. Let's see. Next up, I think I had 2 different cards, if I remember correctly, for coterminals. Okay, so I want to talk to the degree people first because, of course, like I said, things usually make better sense to us in degrees. So what did you remember about coterminal angles in degrees?
So the coterminal angles in degrees, basically, it's the same angle, but it's either positive or negative based on if you add 360 or subtract 360 from the original angle.
Okay, good. I like what Dylan said right there. Coterminal angles are really the same angle, right? So I'm going to be an angle. Is this my initial side? Does this look right to you? I'm about 120 degrees. Okay, so say I'm 120 degree angles and I want to be a different angle, but I want to look exactly the same. The only way for me to do that is to go all the way around, right? So that's where Dylan said either add or subtract 360. I can go any way. And I can do that as many times as I want, right? Getting a workout here. Okay. So I could do that as many times as I want. So coterminal angles, we're going to say, are the same angle, different measure. They look exactly the same, but they have different measures. And in degrees, you can add or subtract 360 as many times as you want. There are infinitely many coterminal angles, angles that are the same. And what did my radians group say? Where's my radians? What'd you guys say?
You just add or subtract 2 pi.
Yeah. If you feel comfortable with these things in degrees, you just have to make the equal substitution in radians. So what's equal to 360? It's 2 pi. So you're adding and subtracting full revolutions. Now, this is an example of a very common way that the question will be phrased, and Dylan kind of referenced that too when he described it. A lot of times we ask you to give us one positive coterminal angle and one negative coterminal angle. So usually that gets done if you just add and subtract 360. You know, if I started you off with 1,000 degrees, to get a negative coterminal angle, you're going to have to subtract multiple revolutions, right? So that is allowed. Okay. But on this one, it's just 2 pi over 5, so I'll do 2 pi over 5 plus 2 pi, and I'll do 2 pi over 5 minus 2 pi. Be really careful on this. That 2 pi is really like 2 pi over 1. So in order for you to be able to add or subtract a full revolution, you need common denominators. So 2 pi is really the same thing as 10 pi over 5. So add 10 pi over 5 and subtract 10 pi over 5. So we'll get 12 pi over 5 and negative 8 pi over 5. So if I asked you to sketch 2 pi over 5, 12 pi over 5, negative 8 pi over 5, all of them would land in the same quadrant, have the same terminal side. The only difference would be that arc that you draw. What direction you go, how many times you go around, that's it. Okay, last one is the arc length and area of a sector. So those are probably the two hardest for the people who got those cards. Are those my last two groups over there? Good job. Both of them have to do with circles. Okay. And an image where you have some central angle. It could be any angle. Some central angle theta. You got some radius. So who is my arc length group? Okay, did you uncover or realize anything about arc length? What it is, what its formula is, did you find any of that?
Kind of like the outside part
How long the outside part is. Yeah. So I always say, what if this were a pizza? Then the arc length would be the crust. Okay, it's the length of the arc on the outside of the circle. It's basically a portion of the circumference. Or a fraction of the circumference. Now, circumference is 2 pi r. Okay. There are 2 pi radians in a circle. So when we do the fraction of the circumference, it will simplify very simply in radians to s equals r theta, which is awesome. That's easy. Take my radius times my central angle and I have my arc length. I'm done. Okay. This only works in radians. Okay. So side note, both of these are true only in radians. Now, there's another formula that you could use. The angle divided by 360 times 2 pi r for degrees, but that one's a lot more complex than r times theta. So I'm going to stick with my radian formula. If I ever get a central angle in degrees, I'll change it into radians, and then I'll just use r times theta. And this group here, you guys have my area. So what's the area?
Well, figured it was like the area of the circle's pi r squared, so we just did that.
Yeah, so it's the same idea. It's a portion of the area of the circle. So area would be represented by the space inside. Okay? And it's only a fraction of that area. So you're going to multiply it by a fraction of the circle. If you're in degrees, that's the degrees divided by 360. If you're in radians, remember that we've got 2 pi radians, and then we're talking about fractions there, it will simplify to this formula. 1/2 times r squared times theta. We're running short on time, so I'm not showing you that actual simplification, but if you want to kind of play around with that in radians, you can. Remember that in order to be able to use both of those, your angle has to be in radians. Make sure you have that written down. The angle must be in radians. Make sure you do your homework tonight. I'll be coming around to check it tomorrow for completion.